Welcome. This is a new elective module. These are like module 7 and 8. These are elective module, and they can fall under the computer modeling and simulation. And we will talk about this. So this basically like what we did in this module was morely physics-based modeling. What we did in this module was physical modeling, and this guy here, module 8, that would be data-driven modeling. Okay, we will talk about this. These are some reference. So if you want more engineering problems, that would be a good reference. If you want to learn more about this conceptual stuff and see in more details uh, and more related topics, you can check this book. If you want really a good reference book when you go in depth and have an in-depth understanding, you can check this reference here. Okay. This module so far has one lesson, which is linear regression. So basically, I will introduce the basic concept of linear regressions, and then we will see an example, like a critical thinking exercise. We will answer these three research questions, like, is the Earth warming or not? And we can answer this with the linear regression. Okay, so that's our lesson, the linear regression. Part 1 is about model selection and model complexity. So by the end of this video, you should be able to understand like how to select the right model for your data and understand the role of model complexity. Model complexity is the number of parameters of the model. So you have a model, like you have a data, you're trying to fit this data. The more parameters you will do, you will improve the fitting. But this could also lead to overfitting, and overfitting has two problems. It has one problem with generalization, and another problem is called like overfitting. And so by the end of this lesson, you will be able to describe why a simple model is better for generalization, and a simple model is better for avoiding the overfitting problem. Okay. So let's just get started. So what we did before, like in module 1, we look at physical model. In module 2 to 6, we mainly looked at physics-based models. So physics-based models, that's when you have a physical equation, and through the modeling process, you just use this equation and parameterize this equation to describe the process that you are interested in. While in data-driven model, you don't have this physics-based equation. You don't have this physical equation. And instead, like you learn from the data. So like you build your model based on the data. So you select a model and then you parameterize this model based on your data, based on the available data, and then you can use this model. So the simplest example of this model is that linear regression model. So you have a data, you think this data is generated by linear processes, and then you simplest thing would be you just fit a straight line to this data, and then this straight line can tell you, you can use it to understand your data or for prediction purpose or for whatever purpose the model is, testing hypothesis, whatever your purpose is. And this would be like data-driven model, like you will learn these things, like if you look like a statistics course, for example, or data science and machine learning course. So that's basically where these topics are covered. But here in this module, I will just for the sake of completion. So we did this guy, we did this guy. So I just want to give you a flavor of data-driven model and some basic concepts for data-driven modeling. But if you want to learn more about like data science and machine learning, then there are other courses for this. So for example, we have environmental data science course. That's where you learn about like data science and machine learning and things like that. Yeah. But here is just like some, like you'll get some good conceptual understanding of these types of model. Okay, so let's just start like what can you do with like linear regression, or why linear regression, uh, why we often use linear regression. So linear regression, because there are a lot of processes that have linear relationship. So for example, like a classical example when learning linear regression is it tells you what is the relationship between ice cream sales and temperature. Is there a relationship between ice cream sales? Like you have a shop that sells ice cream and you want to model based on temperature how much ice cream you're gonna sell. So is there a relationship? Yes. So here basically you put here the temperature, yeah, and you put this is called like the independent variable, and you put here the ice cream sale, and that is your dependent variable. Dependent variable. Why this is independent? Remember we did this already. The independent because it is its own thing. It just do whatever it's doing regardless of anything else. So the temperature will increase or decrease, yeah? But the ice cream sale, it's dependent because it depends on temperature. If the temperature, so here like you see this relationship, if the temperature goes up, for example, then the ice cream sale will go up. Yeah, so you see here positive trend. So this is called like a positive trend. Positive trend means as my independent variable go up, my dependent variable will change accordingly. Here we only have one uh, independent variable, but you can have many. Like you could add like temperatures, that's one of them. You could add like rainfall. Yeah, rainfall. You can model how my ice cream sale it changed with temperature and rainfall. You can also add like vacations or like vaca I have technical issue with my pen. It's not responding. You can have like vaca yeah, vacation, yeah, vacation or like the day, yeah. So this here, like when you have more than one independent variable, this will you will not be like a single variable regression, but that would be multiple variable regression, yeah. So here, that is a positive trend, means that when my temperature go up, my ice cream sale could go up. Yeah. This is another example where there is no trend because, like you see the data here, there's really no clear trend. These are just some random fluctuations. So this goes up and then up and down and up and down, up and then down, up and up and down, up and down. So you don't really see any clear trend. So here, that would be no trend. So here, for example, which means like my dependent variable here, y, does not depend on my independent variable here, x. It's not dependent. It is like, for example, like you look at, whatever, like something that's not related to ice cream sales. Yeah. Uh, so you look, for example, like ice cream sales at my city. Yeah, my city with like temperature at uh, New York, for example. Yeah, I don't know what's wrong with temperature at New York. So there's no relation because in Florida, for example, the temperature, like my ice cream sale in Florida, will not depend, for example, on the temperature in New York. Yeah. Or somewhere. Yeah, it could. I mean, there could be a relation, but like this is just an example. Here is another. Also, is like you could also have like a negative trend. So negative trend means like this is my independent variable and this is my dependent variable. So like you can see here, for example, like this is contamination, and then like here, for example, like house prices. The house prices. So here, for example, you can find like you have like a contamination in urban lakes. Yeah. So you have like a contaminated urban lakes. That could be the level of contamination, and that would be the prices of the house. So as the level of contamination will increase, your property value or house value will decrease. So you will have, this is like a negative trend. That's a negative trend. Okay. So here you could have like a positive trend, you can have no trend, just some random error or fluctuation, and then you can have a negative trend. Okay. Delete this here. So now I can choose, like if I want to model this to see like as at this temperature how much ice cream I will be selling, for example, and at this temperature how much ice cream I will be selling, for example, you can fit a linear model to this. So here the positive trend, like I fit a linear regression model. So you see my model here is about like 2.5x. So that basically this 2.5 lines, that is the slope. So here that tells me like the slope of this guy, and 6.9 that tells me the intercept. So if I extended this line uh, to my x-axis, it will intercept here at 6.9. Yeah, that's the intercept. And what is this R squared? This is called the coefficient of determination. We will talk about it, but basically this tells you about the goodness of it. Or it basically tells you like how much my independent variable, explains the variance of my dependent variable. So if my independent variable can explain like this variance, you see here, this variance, see this variance of my independent variable, then you will get a high R square. And that also tells you about the goodness of the fit, like how far these residual are from my model. Yeah, because if these residual are far away from my model, then you will also, this means that this model cannot well explain my dependent variable. Like here, for example, if I took like the derivative of this guy, like so if I said like dy by dx, that would be equal to what? That would be 0, and here I will get like 2.59. So that's the rate of a change or the slope of this line. Versus here, like you see here, this is the equation that I got. It's almost like 0 here, and this is the intercept here. Yeah. And see the R square is almost 0. Why? Because there is no relation, there is no trend. So basically, like this guy cannot explain the variance the variance of my dependent variable y. So you got no trend. If I got the derivative of this one, like dy over dx, what do I get? I got like 0.09, which is like almost 0. There is no rate of change. Yeah. There is no trend, upward or downward trend. Now, like the last case, I could fit like a linear regression model. Yeah. And basically, you see here my slope is negative. So now my slope is negative. That is my slope. I have like a negative slope. My intercept is about like, so like if I extended this line here, so my intercept is like 33.4845. That's like my intercept here, and my R square is very good because like I have a like strong negative trend, and basically like my X can explain well the variance of my Y, like the variance of this data, the variance of this data, and I have like this trend here. So you see here I got like an, don't worry like about the coefficient of determination. We will look at this in details in the next video, but here just use it as a metric to study the goodness of the fit. So here you have a good fit. This model can explain the data. Here you don't have a good fit. This model cannot explain this data. And here also you have a good fit. This model can explain like this data and like the trend of this data. Okay. What am I showing you here? This equation that I'm showing you here. Actually, this is my true model. Yeah. So let me delete all this. That's my true model. What does this mean? So basically, like, let me delete this here, make it clean. See, this is the model that I estimated through my regression, but that's my true model. So basically, to generate, how did I generate this data? I just use this model. Like I created, like I have an equation for straight line, and then I put some random error to it. So this random error, I sample this from a normal distribution with a mean of 0 and standard deviation of 2 or variance of 4. So basically, this tells you about the mean and the variance. Yeah. So I have like an equation of a straight line, and that's how I took like all these random samples. So I took about 20 or whatever random sample here, and then when I fit, so we know that these are generated by a random process because here's a random process, but it has a big error. I added a big error, so you see like this is a big error, like a variance of 4. That's a big variance. Okay, or a big standard deviation. So this is like a linear data generated from a linear process, but it has a significant error. And why do we have a significant error? Because that could be like measurement error. Like for example, I want to see the relationship between, like let's assume that my dependent variable here is like nutrients, like total nitrogen, and my independent variable is like harmful algae plumes. Yeah, and I want to see the relationship between total nitrogen and harmful algae plume. Like when the nutrient increase, do we get like more of these guys, for example? I mean, this is just a hypothetical example. Yeah, and then you see that like when this guy increase, this guy will increase. But when you do, like when you record this data point, so here basically like at this at this concentration of total nitrogen and this hap, like when you put this data will not be accurate. Why? Because there's measurement error when you measure this, there's measurement error when you measure this. Yeah, so there would be like some measurement error, for example, or just random fluctuation in your processes. Yeah. And that's why you always, like your data always have an error. Yeah, some type of error. So when we fit a model here, like you see the models that we fit here is not bad. Like here, like this model has a slope of 3, this model has a slope of 5.9. I mean, not bad. This model has an intercept of 5, this model has an intercept of 6.9. I mean, it's okay. So basically that is the model that I was able to fit. So that's how I was able to retrieve the original model. Similarly for this guy, like what model did I use? I just generated like a random, like straight line, a vertical line, because y is equal to 20. And I just put some noise to it, like some noise here, 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 here. And that's how I get this data. So it's just a straight line with some noise to it. And for this one, the true model, it has like slope of -3 and intercept of 35. And this is my regression model. In real life application, this model, we don't know it. Like in real life application, we don't know this model. We don't know like this model. We don't know this model. But here we know this model because this is the synthetic data that I just generated from this model. In real life, this data will be measured. So you'll go to the field or you wherever you have an instrument that measures this data for you, and this model is unknown, and that's what you try to estimate through your regression analysis, for example. Yeah. Okay. Uh, so that's basically like one like what we do like with regression analysis is that like we can understand like the trend of the data, and to what extent can my independent variable explain the variance of my dependent variable. Yeah. Okay. Uh, So now selecting the right model for your data ensure accurate projection. So like look at this data. So this data, like you might look at it, you don't know. Maybe you will say, somebody will say, okay, maybe this data is generated from a linear process. Another person will say, oh, maybe this data is generated from a line. Like he will say, okay, maybe it's generated from a linear process and I can fit like a line that looks like this. Yeah. I mean, doesn't look very much like a straight line, but it might look something like this. Yeah, I can fit the lines that look something like this. Another person will say, you know what, that doesn't really look linear to me. That could be like a non-linear process. It could be something that looks like this with a little bit of curving. So it could be non-linear process. Yeah. So you need to be careful about like selecting the model, like whether like fitting a linear model is the best choice or fitting other types of model, like a non-linear model, whether this is like a parametric model or non uh, or other types of model. Yeah. So look at this data. So basically this data, maybe somebody could explain it by like linear model, or somebody will explain it by maybe like a little bit of non-linear reality, like a quadratic equation or something like this. Yeah. But this data, does this data looks like linear to you? Like if I fit a linear model to it, it will probably not fit. It will be like something like this, which will give me an r square of 0. Yeah. Just a straight line like this. But maybe this data would be better fit by some type of periodic model, because I see some periodicity here. I see something that's going up and then going down. So I see something like going up and then going down, going up and going down, and going up and going down. So that might be a better model for my data. I fit it by like a non-linear model, and especially a model that has some periodicity, like some periodic that keeps repeating periodically, and that's like a trigonometric function, like a sine function, for example, or a cosine function, or something like this. Yeah, something that's periodic, that has this periodicity in it. So here, for example, actually this data, I generated this data from a linear process with significant error. So in this data, I had a linear model and I put so much error to it, and that's how I got this data. This data, I actually generated this data from a nonlinear process with significant error. So again, like for this data, I used a nonlinear model to generate it, and it had like a significant error to it. So for this one, it's not bad to fit just like a linear model to it. So here, if I fit this linear model to it, that's basically how it will look like, how this model would project. Like if I want to project this phenomena in the future, so here, this is at 0, like 2, 4, 10. If I want to project this to 12 and 14, for example, so that would be like the projections. That's how it will project in the future. What r square did I got? I got an r square of 0.8. I mean, not bad. I mean, which means that this data can explain big part, like my independent variable x can explain big part of my dependent variable y. Yeah. So, and I got these equations that I got, like this is the slope and this is the intercept. Yeah. But for this data, I didn't fit it, like I knew that this is not a linear model, so I just fit a non-linear model to it. I fit like a sine model to it. So here, this is the sine function that I fit to this data, and this sine function had so this model has how many parameters? So this model has one, two parameters. So it has like B0, for example, and B1. So this is called like 2 parameter. Yeah, this is 2 parameters. This model has how many parameters? So like if you look here at this model, it has like one here, another one here, another one here, and another one here. So this model has like 4 parameters. So this 4 parameter model, and see now can was able like to describe this data. This model, because it has 4 parameter, is called like this model is more complex than this model, because this has 4 parameters, so it's more complex than a model that has 2 parameters. But this model, if I did future projection with this model, that's how it would look like. And that's probably how the data would look like. Versus if I use a linear model, the future projection would be something like this, just linear. Yeah. But here, the future projection would be something like this, which would most probably, like if I started collecting data in the future, it would probably be somewhere here. That would be my future data. So you need to be careful whether like a linear model is the best choice for you, or you need to use a non-linear model. Yeah. Now, uh, but if you want to choose like a non-linear model, you need to be careful, because in that case, like in that case, a linear model is a good choice. In that case, a non-linear model is a good choice and is actually justified. But in other cases, it is not clear whether like a linear model is a better choice and justified or not. And I will show you this. But before I show you this, I just want to show you that this model was actually created from like this data was actually created from a linear model. So I use this model and I added this error to it, and that's how I got like these different data points that you see here. But see, the variance is huge. I have like a variance of 9, like the standard deviation is 3. So I had this model and I add a huge error to it. So probably the original model was something like this. That's starting at 3, and then this is the data that I created from this model. Now, guess what? This one, I actually use the sine function to create it. So fitting a sine model to it, that was also a good idea. Yeah. And you see, like this is my original model, this is my regression model, and you can compare them. Okay. So now let me show you, like if I have this data, which was generated from a linear process. Again, the data has huge error. Why the data has huge error? Because as I mentioned, like we have some measurement error, and that's why the data has a big error. But or there could be just some random fluctuation. That's why like the data has like a big error. But the underlying processes, it's a linear processes. It's just like a big error, and that's why the data might seems like a little bit non-linear. But the underlying processes, it's just like a linear processes. Okay. So if I fit this with like a non-linear model, just pause the video for a second and think about it. What will happen if I start to fit this with a non-linear model? So let's look at here. I'm like, this is my data. This is, I just like generated it. Oops. Data. I shouldn't show you this one. I mean, just forget about this. I mean, this is, shouldn't like, forget about this. Don't look at it. Or you can look at it. I mean, you can know this. I can give you this piece of information. Actually, this data, we know that this data was generated like from a linear processes, but without this information, when we just look at this data, we wouldn't typically know if this is generated from a linear processes or not. But actually, because I gave you this equation, now you know that this data was generated from linear processes with a very big variance, like a huge variance. Yeah, that's why it looks a little bit, might look as like a non-linear. So now I will show you, like if I fit a linear model to it. So here, if I'm fitting a linear model to it and I'm showing like the root mean square errors this time, I'm not showing you the R square. The reason for this, because let me tell you about this here. Like you see here, for this one, the R square is 0.7, the R square here is 0.95. Usually the R square is not a very uh, like when you use it for a non-linear model, you should use it with a grain of salt, because it might not very well explain the variance in the non-linear process. Okay, so you can use it. I mean, just as like just an initial guideline to tell you how about the goodness of it, but you cannot really use it in as like a rigorous metric for comparing a non-linear model. And when we come to comparing non-linear model, I will tell you what would be a better matrix than using R square. Okay, so for this comparison here, because I will be comparing like different models. So here I looked at this data, and then I would say, okay, the best thing maybe to fit this data would be I will just like use like a first degree polynomial, which it would be like a linear model. So I got this and I got this root mean square error. And you remember what the root mean square error is. So root like error, that would be like, so this is your data point, this is your model observation, and that, if you remember, that's called like the residual. So that is the residual or the residual error, or that's like your error. So if I got like this, like this, so that is like the uh, y at a point like I observe it minus y I, like at any of this point, like at this point I, so that would be I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5, and so on. Y, like the model, that is the error, like the difference between like my model and my observation. So here it would be large, here it would be very small, here it would be large, here is very small, here is very small, here is like something, here is like something. That's this error, yeah? So you get the difference between the observation and the model, and then you square them. Why do you square them? Because if you didn't square them and you sum them, the positive error will cancel, like this guy, for example, will cancel with this guy, and then you will think that I don't have any error just because they canceled out. So what you do is that like you square them, and then after you square them, you sum them. So you you sum them, you take like summation from I is equal to 1 to n, whatever, like 1, 2, 3, 4, 5, 6, 7, 8. So in that case would be like 8 and then divided by, or n, I mean, you can just, and divided by n, because, and then you take the square root. That's called like root mean square error. So the error is like this guy, the square is this guy, the mean is like this guy here, like you take the mean of all the error and then you take the root at the end. That's why it's called like root mean square error. Yeah. So here I'm using like a root mean square error. That might be a better metric. I mean, it's not perfect. I mean, it's not a good metric also, but it might be clearer metric to compare like different models. So here, this I will, here I'm fitting a first degree polynomial. Here I'm fitting like a second degree polynomial. So second degree polynomial is just like x to the power 2, first degree polynomial x to the power 1. So here I have like, this is my beta 0, beta 1, and beta 2. I have 3 parameter. Here is like my beta 0 and beta 1 and beta 2. So like you see the root mean square error, the error is improving a little bit. So you see the error is improving because this line started to curve a little bit and get more close to my data. Now, if I use like a polynomial to a degree of 4, so I have here x to the power 4, then how many parameter will I get here? I'll get 5 parameters. So I have like beta 0 here, beta 1 here, beta 2, beta 3, beta 0, and beta 4. So I have like 5 parameters. So this model has 2 parameter, this model has 3 parameter, this model has 5 parameter, 2 parameter, 3 parameter. This model here, degree fifth, has like 6 parameter, and this model like to the degree 6, that will have like 7 parameter. Okay, and like you see here, this model like is perfect fit for my data, and sees my root mean square error is very small, and here sees my root mean square error is very small. So like if you compare to this guy, this is like 3.3, and this is uh, 0.49. If you are using r square, for example, like the r square for this guy would be maybe like 0.8, and the r square for this guy will be like uh, 0.099, like very close to 1, like a perfect r square. So r square goes from 0 to 1. That's the maximum value. Okay. Uh, so which model are you going to select? Yeah. So are you going to select like a linear model, like with 2 parameter, or you're going to select like a slightly non-linear model with 3 parameter, or like a more linear model with 5 parameter, or this guy who has like a very like small error and fit my data perfectly? So if you are a non-experienced modeler, what you will do, like you will be fooled by like the R square value, like of, or like the small root mean square error, or like the R square value of like 0.99. But if you are an experienced modeler, you might know that basically this model, what you are doing here with this 6-degree polynomial, you are just fitting noise and random fluctuation rather than the true underlying linear relationship. Here, I am fitting the true underlying linear relationship, because if I and you, and this you get from experience, because if you know that your data has like a kind of a linear relationship, then fit a linear model to it. Because here I am fitting the true underlying linear relationship, while here I'm just fitting random fluctuation and noise. So according to something called like the principle of Ocean razor, it states that the simple explanation is usually the best. So simple means what? Like the explanation that has less parameters, less degrees of freedom. So here I only have 2 degrees of freedom to fit this model, like this guy and this guy. And this guy I have 7 degrees of freedom to fit this model. So it has 7 parameters. So this is a complex model because it has simple 7 parameters. This is a simple model because it only has 2 parameters. So according to the principle of Ocean razor, the simplest explanation is usually the best. So a linear model, this guy will generalize better with new data points generated from the same underlying linear processes. So if this is a linear processes and then I collected more data in the future, or like at more points here, this data will be somewhere here. Yeah, so if I extended this model, it will just fit this data. Versus like this guy, it might shoot like down there, something like this. So it will not fit my future data. And allow me to show you this. But that's the main thing. Like this guy, for future data, this one will generalize better because here I'm honoring the process, the true process of the model, while here I'm not honoring the true process at all that generated this data. I'm just fitting random noise and fluctuation. So if the underlying processes is linear, the true the true model is linear, which is actually the case because I generated this data from a linear model. So if the true model or the underlying processes is linear, then this linear model would be the only model that is unbiased, and all these other models, so that would be unbiased. Even though it does not have a good fit, it will still be unbiased, versus this one will be biased, this one will be biased, this one will be biased, this one would be biased, this would be the most biased one, and this would be like the least biased one, and this would be like this would be, and this one would be less biased than this one. So like the linear model would be less biased than this one. And usually, how do we compare like model with different complexity? Like how could I compare uh, like to know which is better? Like model, like I have a data, so this is the data. Usually we don't know this. I just didn't hide this, but usually we don't know this in advance. And then I have like this data and I fitted like these 2 models to it. How would I know which model is better? Like, is this a better model or is this a better model? So usually there are other metric rather than like R root mean squared error or R square. So these other matrix, for example, one is called like Bayesian information criteria or KIC. And these matrix, what they will do, they will reward the model for the goodness of it, of how it can explain the data well, by like high R square, for example. But it will penalize the model for the number of parameters. So if the model has a lot of parameters, it will be penalized for this. If the model has less parameter, it will be rewarded for this. So that's like called like PIC. Even BIC and KIC and like these information criteria, they are not even reliable and they are not very accurate. And the most, like if you want to do this accurately and rigorously, you have to do Bayesian statistic and calculate something called like Bayesian model evidence. And we usually do this with Markov, like Monte Carlo sampling. Markov, particularly something, a technique called Markov chain Monte Carlo. MC, if you have heard this term before. And so if you did Markov chain Monte Carlo and you calculated the Bayesian model evidence, this Bayesian model evidence will help you and will tell you, like, select this model and don't select this model. Hopefully, yeah, it will tell you this. If you uh, if you don't have like a big error, which is in that case you have a big error, it might be confused also, yeah. But hopefully, like, if you did this, it will tell you like this is a good model to go with. Definitely not this one, yeah. It might tell you this one is okay also, yeah. But let me show you like how this one would generalize better, and how this one, like, by overfitting my data this way, how will this lead to not only like wrong parameter estimation, like all these parameters are wrong. Like here, like, see, this parameter is like 2.25, very similar to my true slope. This is 5 something, very similar to my intercept here. So all these parameters might not be accurate. So it's not only you will get bias parameter estimation, but you will also get bias projection. Allow me to show you. So here, this is the data again. I'm not showing you like which process. So this is the linear models that I fit to the data. And this is the nonlinear models that I fit to the data. So if I believe that this data follow like a linear processes, and the underlying like linear processes, and it should be uh, modeled by a linear model, when I do future projection and I compare this with future data that I didn't use to train this model, data that I didn't use to make this model, it should fit good for future data, versus this one for future data, like data that this model never sees, that I didn't use to train this model, it would fail for future data. So let's see this. So here I'm just like, these are future data. I generated this data from the same original models that I generated this data, except that this data was never used to train this model. Like, this data was never used to come up with this equation. So this equation was just developed just like using this data, and this is a new data. So you see like how the model is passing well like through the new data. So the model can really explain the new data, versus this model, if I projected it for the same period from like 10 to 14, if I projected it from the same period, see, it's a complete failure. It's a huge bias. So this goes from like here 0 to 40. This goes here from like 40 or whatever, like all the way to like this weird number, uh, negative 305. So you see here like how it's like a total failure. This is because it's called overfitting. So when you overfit your model, you basically fit the model not to the true processes but to random fluctuation and noise. Your projection could be very biased, as this model show, for example. Okay, so that's all what I wanted you to learn from this video. So let's do the take home. Two big take home. Select the right model for generalization, because even if your current data has a big error, but future data might have less error. So here, like, see the truth, like this data, like my initial data here. So this is the model that I use to generate this data, like the current data and the future data. But even if your current data, like your current technology, cannot measure this process accurately, but your future data could be more accurate. And it will, like, instead of having this variance, for example, it could be just like very close to the future projection. So uh, so so this model generalized very well, like, because here, what do I mean by generalization? By just showing this model to a data that it didn't see before, it was able to reproduce it. Yeah, it was able to reproduce it very well, and describes this data very well, versus this model does not generalize well at all. I mean, for future data, it failed. Another thing, avoid over parameterizing your model by just keep adding more parameters, like 1, 2, 3, 4, 5, 6, 7, by just keep adding more parameters to avoid biased prediction, because you get biased prediction. So here you learn it two things. You learn it about like how a simple model would better generalize than a complex model, and the simple model again is a model with less number of parameters, and then how a simple model will be less biased for future projection compared to complex model which you just fit it not to the true process but you just fit it to the random fluctuation and noise. So that's all what you need to know. So be careful about like before you select like a more complex model, like move from a linear regression to something that's like non-linear. First, look at your data carefully and see if you can describe this data by a linear relationship, and you know that this data follow a linear relationship, like sales of ice cream and temperature, for example. Then use a linear relationship, even though a linear relationship uh, might have like smaller root mean square error than the nonlinear relationship, or smaller r square. So like the r square for this one, I think I calculated is like 0.8, and the r square for this one is like 0.9. So even though like this guy has like smaller r square and larger root mean square error, is still preferred than this guy who has a higher r, like better r square and better root mean square error. Okay, so that's all for this video, and then in the next video you will learn how to actually do this guy, like how to fit this straight line to my data, and how to find this best fit, like which the lines that best fits the data. That's what we will be learning in the next video. And also, most importantly, we will be learning about like this r square. What is this r square? What's the meaning of this r square?